So in chapter 4, we're going to be taking a look at two new function families, so parent functions. The first of which here is what we call an exponential function. So you see the word exponent there within the word exponential, and the idea is these are functions where we're going to find our variable x is actually in the exponent of the function. So these behave very differently. We've not seen these up to this point. So the first list here, you see these are 6 different exponential properties. These are ones that hopefully you are familiar with and would have been things you would have seen in potentially previous algebra classes. Just different rules on how we can combine similar bases by adding or subtracting the exponents based on multiplying and dividing. A couple different rules for simplifying exponential form where there's parentheses involved, and one where there's just this understanding of what a negative exponent represents and how we can rewrite it if we're going to perhaps do something with it or even put it in a final form. So we will see all those different rules show up here and there throughout the section. It's the chapter. So for our first example, just really, if nothing else, to introduce this idea even to the point of how to find it on our calculator, because at times we will need to potentially approximate values here. Doesn't happen often, but in an example like this, we've got the scenario that this function f of x 42.2 times 1.56 raised to the x models the average amount spent. So f of x is representing dollars when you've been at a shopping mall for x hours. So x represents the time that you've been at the mall. So the question is, what is the average amount spent to the nearest dollar after 4 hours? So in this question, they're asking for the average amount, which we said is our function value. They're telling us the value for the number of hours, which is x. So this is nothing more than a question of, we say f of 4 equals 42.2 times 1.56, and we're going to be putting a 4 up there to the 4th power. So to do this, you definitely need a calculator. I'm going to show you the button that exists on graphing calculators, and then we'll talk about the other button that can be used. So this little caret symbol, this is the way we will be allowing our calculator to enter our calculator exponents greater than 2 for the squaring. So for this particular example, we would just need 42.2 times 1.56 raised to the 4th. That little button there is telling your calculator the next thing it sees is an exponent. So there is the screen after I type it in, 42.2 times 1.56 raised to the 4th. Your calculator will follow just basic order of operations, so it will know to do the exponent first and then the multiplication, as would be implied here in the problem. So I hit enter. So there's our value, and it did say what's the average amount to the nearest dollar. So if we just say we're going to round that, 249.9 would round up to $250. So that would be the way to use the graphing calculator or any calculator with that, what we call caret symbol. If you do have a calculator other than that and you see a button, it might look like a y to the x or x to the y button. If you see either of those, you want to put your base, this number, first, then hit that button, then type your exponent, and then hit enter, and it should default to base raised to power, and you should get your final value there. All right, now let's talk a little more about this exponential function as a function, and thus it has a graph. So what ends up being the case is the exponential function family actually has 2 different graphs. So we've got the function f of x equals some base, b is standing for the base, raised to a power. Now you'll notice we're going to say that the base is any number larger than 0, so some positive number, okay? These are the graphs for a base that's positive, and specifically make sure that that base isn't the number 1 exactly. The idea behind this is if you had 1 raised to a power, that would be 1 to any exponent would always be 1. You'd have nothing but a horizontal line at y equals 1. Would not really be an exponential function in that sense. Exponential functions should have this idea of growth or descent, depending on which one you're looking at. So notice these 2 different graphs are both graphs of the exponential function, but what changes is whether or not the value of b, the base specifically, is a number that's larger than 1, or it's a value between 0 and 1. So in other words, a fraction or a decimal value that falls between 0 and 1. And again, like we said, we don't want 1, right? 1 would be boring. We also don't want 0, right? We're not going to use 0 because 0 to a power would also be 0. So aside from 0 and 1, starting at 0, but above it, anything between 0 and 1 has this shape. All values of the base above 1 would have this shape. Now we'll get into more about that, and we'll see that pattern, why that happens on the next page in a couple examples. But here's just a list of the basic characteristics of these functions, everything we've talked about before. Both functions are one-to-one. Remember, that means they're passing the horizontal line test. Both have a domain of negative to positive infinity, right? You could put any number you want up here for an exponent, raising it to a power. Either one would be fine. Now the range, notice, with this graph, what it's doing, something we talked about in the last chapter, it has that asymptotic behavior. It's asymptoting to where it's not going to cross this x-axis on this side for this graph or on this side for that graph. Okay? So with that behavior, notice the range is 0 to infinity. Again, if we're thinking about this b being a positive number, if you take a positive number to any power, you get a positive number. There's no way to get any negatives out of a positive number to a power, right? In fact, since we're excluding 0, you can't get 0 either. There's no way to get 0 out of this. So that's why we're going to have all positive y values for our range. Now the big difference is the increasing versus decreasing, right? Here it's increasing left to right. Here it's decreasing left to right over the entire interval, negative to positive infinity. And then the asymptotic behavior is referred to. The only difference is here y approaches 0 as x approaches negative infinity. Here, y approaches 0 as x approaches positive infinity. But other than that, they share very similar characteristics. Notice a very important point, the point 0, 1. We'll even see this as an official rule, but we can just talk about it. Why does this point exist no matter what? Well, if you imagine 0 as your x value, and you plug in a 0 for x, anything to the 0 power is always a 1. That's just a standard global rule for exponents. So any non-zero power, non-zero base, to the 0 power will always be 1. So you'll have this point 0, 1 on either graph no matter what you're dealing with, no matter what's your base. Now the difference is here we have the point 1 comma b as it's increasing. Here we have the point 1 comma b as it's decreasing. So again, because b is bigger than 1, it's above, or b is between 0 and 1, it's below. So it still works. It's still consistent, but obviously it does create a different picture. So we'll take a closer look at why these graphs happen the way they do, kind of what the pattern's going on here on the next page.